Hey, Jonathan.
How's it going?
Good. How are you?
I'm doing all right. It's not Friday yet, so
Almost there.
Yeah.
Is your last lecture today?
One more after this, and then that's it.
Nice.
Yeah. And then, do you know if people were able to figure out the remote, the Microsoft's remote?
I hope so. I didn't hear back from anyone else, but so I presume it worked for them. But we'll ask. I'll ask today and see.
And then we don't have anything due this class, right? Until
Tuesday. Tuesday, yes.
Okay.
Yeah. So the first ANSYS activity is due on Tuesday.
Okay.
Okay, it's 4 o'clock, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today?
Pretty good, thank you. How are you?
Good, good. Thanks for asking. Okay, so the plan for today is that we're going to continue on with the lecture notes that we started last Thursday, actually, which is on the stiffness method. Okay. So I don't think it'll take us the entire time to finish these up, but I do want to make sure I finish these up before we get into trusses next week. But you know, since I think we might end early today, I do want to spend some time to help people debug their answers a bit more, because I know a lot of you guys had some issues last week. So if you're having some trouble completing the activity, or if you didn't, end up with the simulation result by the end of Tuesday, go ahead and save your questions for the end of today, and then I'll be helping people out with that. Okay. Okay. So are there any questions on anything before we get started today?
Are we opening up the project from Tuesday?
No, we're not. So if you finished up the activity, or at least got to the deformation and the stress results,
Yeah.
then you're good to go to do the other stuff. But we're going to be starting something else today. But if you're still having some issues, then I'll help people out at the end of class.
Got it. Okay.
Mm-hmm. Okay. All right. So let's go ahead and continue off where we left off. And so just to kind of remind you guys, we were doing or working with this thing called the direct stiffness method. Okay? So this is kind of in the vein of the of kind of the theory and the concepts behind finite elements. Okay. Because even though this class we'll be working with ANSYS a lot through all the activities in the final project, part of learning finite elements is also learning the theory behind it, right? And the direct stiffness method is kind of the best place to start because conceptually it's the easiest one to do because there's kind of the least amount of steps. Okay. I also like the direct stiffness method because it builds off a lot of information that at least mechanical engineers have seen before in their previous classes. Like in this case, we are looking at springs, right? So a lot of people have been exposed to springs probably at some point in their science or engineering education, right? And so we start off with a spring like this, okay? Right. And the only material property that we know about the spring is its spring constant, and so we usually give that the symbol K, right? And then what we did from here was we labeled both ends of the spring, okay? And so we have the left side of the spring we typically give, I'll give that node number 1, and on the right side of the spring will be node number 2, okay? And then on each node, we've characterized basically 2 things, okay? And so in the first case, we've characterized, how much the spring displaces, okay? And so we use D1 and D2 to specify, how much the spring is either moving in this case, in the positive X direction, okay? And so that's one thing that we can characterize. And the other thing that we can characterize is the forces that we're applying on the spring, okay? Okay. And so we denote the forces F1 and F2, okay? Because we know that, whenever we apply a force on a spring, it's either going to compress or stretch according to its spring constant, okay? Okay. And so where we left off was we formed a mathematical relationship between the forces and the displacements on the spring. Okay. And that mathematical relationship took this matrix form right here. Okay. Right. And so on the one hand, we have our 2 nodal forces, and so we have F1 and F2, and those are going to be placed within a vector. Okay. Then we had a matrix right here. Okay. The matrix contained the spring constant, right? And so we have K, minus K, minus K, and K. Right? And then we had a vector for the for the displacements. Okay. And here was kind of our matrix system that describes the physics of the spring. Okay. And then each of the vectors and matrices here have a specific name, right? And so, for instance, this one right here is the element forcing vector. Okay. This one right here, which is probably the most important part right here, this is the element stiffness matrix. Okay. And this last vector right here, this was our solution vector. Okay. Because in these finite element systems, we're always going to be solving for, something, right? And so if we look back to our ANSYS activity on Tuesday, what we solved for essentially, or the first thing that ANSYS solved for was the deformations in the plane, right? And so it's solving, in that case, it was 2D, and so it's just solving for the X and Y displacements. But in this case, since we have just a 1D spring problem, we're solving for just the 1D displacements, okay? And so a lot of finite element systems, they, finite element formulations, they take this kind of form where we have a forcing vector, which describes any kind of external effects that we are placing onto our elements, okay? It describes a stiffness matrix. And so remember, the stiffness matrix has any kind of material or geometric factors of our part, okay? And then it also has a solution vector, which is eventually what we want to solve for, okay? And so, this is kind of where we left off last week, which is, we have this one element system. And so what we're going to do today is to see, how can we take this one element system and start to add more elements to it and see how we can actually, put these things together and actually solve a full kind of finite element problem. Right? All right, any questions on this before we go on to a 2-element example? Okay. All right. And so now let's do kind of a worked example, but kind of still theoretical, of a multi-element system. Okay. And so in this example here, we're going to have 2 springs, and they're going to be connected end to end. Okay. And so we're going to have spring number 1, just like that. Okay. And they're going to be connected at this point right here. Okay. And now we have spring number 2. Okay. And so we'll call this first spring, we'll call it spring A. Okay. And so spring A, we'll say that it has a spring constant Ka. And then spring B will have a spring constant Kb. Okay. And so Ka and Kb can be the same, but we're doing this generally right now and just saying that they're going to be different. Okay. All right. And so another thing I'm going to label here are all of the nodes. Okay. And so by nodes, what I mean are, are the 2 ends of the spring. Okay. And so the very leftmost one, I'll give that the number 1. And so that'll be node number 1. The point at which the 2 springs connect, we'll call that node number 2. And then on the right side node, which is kind of free hanging right now, we'll call that node number 3. Okay. And so this is kind of a convention that I'll use throughout the class, where I'll use letter subscripts to denote different elements, and I'll use numbers to denote node numbers. Okay. Okay. And so, when we apply external effects onto these springs, like forces and constraints, they're going to displace. Okay. And so let's actually apply some forces here, and let's apply some constraints to kind of make this a bit more interesting. Okay. And so on the right-hand side, let's apply a force, right? And so what we're going to do basically is that we're going to basically grab that end of the spring and kind of pull it to the right. And so that's going to be our applied force, right? Okay. And then just to make sure that our spring doesn't, start traveling, right? We're going to fix our spring to the wall, okay? Or in other words, we're going to apply a fixed support, okay? And so if you remember from our ANSYS activity, when I say fixed support, all I'm doing is making sure that the displacements and the deformations are going to be 0 there, okay? And so we're basically bolting a spring to the wall. So that node right there can't move, okay? Okay. And so what we're interested in this system is how are all of the nodes going to displace, okay? Okay, because each of these nodes have a displacement that we can eventually compute, right? And so that's going to be D1, D2, and D3. Okay. All right. And so this is about as simple of a finite element problem that you can formulate, right? But even with this kind of simple problem, we'll kind of run through all the steps of forming the element stiffness matrices, assembling them together into one system, applying boundary conditions, and then solving the linear system. Okay. So even though this is simple, it's going to highlight kind of the recipe that we're going to be using for the next few weeks. Okay. All we're going to be doing after this is kind of adding different kinds of elements and more complexity to this process. But this process itself is going to be the same, all throughout. Okay. All right. Any questions so far on the just the setup of the problem? Okay. All right. So let's go ahead and start solving this. Okay. And so the first step that you should do in any kind of finite element problem that you're working by hand is to write out the element stiffness matrices for all the elements. Okay. Okay. And so in this particular case, we have two elements. And so we're going to write out the element stiffness matrix for both element A and for element B. Okay. So let's start with A. Right. And so we're going to use basically the exact same form that we have here, except that instead of just a generic K, we're going to plug in the spring constant for that element, which is Ka. Okay. And so the element stiffness matrix can be F1, F2 is equal to Ka minus Ka minus Ka, Ka, right? And then the solution vector for element A is going to be D1 and D2. Okay. Right. So that's pretty straightforward. We're just applying our formula. Now let's do the element stiffness matrix for element B. Okay. Okay. And so for element B here, I want you to notice that element B is connected to node 2 on the left and node 3 on the right. Okay. And so when we plug into our formula here for the element stiffness system, then we need to account for that. Okay. And so the forcing vector is going to look like this. Okay. And so instead of F1 and F2, we're going to have F2 and F3. Okay. Because those are the left and right nodes. Then we have the stiffness matrix, which is comprised of the spring constant for that element. Okay. And then we have D2 and D3, which are the displacements for the left and right nodes on that element. Okay. All right. So this part, for the most part, is going to be plugging and chugging for when you write out these element systems. But you want to make sure that you write down the correct nodes that they're connected to, okay? And so for this case, we just have 2 elements and 3 nodes. But once we start getting to more and more complicated systems, it's you have to really kind of pay attention to which nodes are connected to what, okay? Okay, any questions on this so far? Okay, all right. And so after you write down the element stiffness matrices, the next step in the process is to assemble them into a global system. Okay. And so the reason we do this is so that we can solve for all of the nodal displacements at the same time. Okay. Because right now, we have 2 separate systems, and their solutions actually depend on each other. So we can't actually solve them, like that. And so the way that we do this is we kind of form one big, linear system in order to solve for everything at the same time. Okay. And so our global system looks something like this. And so on the one hand, we have our global forcing function. And so it's going to be F1, F2, and F3. Okay, so those are going to be all the nodal forces. Next, we're going to have our global stiffness matrix, okay, which we're going to fill in a bit. That's going to be the big part of that. Okay. Okay. Then we have our global solution vector. So this is D1, D2, and D3. Okay. And so that's ultimately what we're going to be solving for. Okay. And so just to kind of help us out when we're assembling the elements, I'm going to label the columns too. Okay. And so this first column will be the D1 column. The second column will be D2. And the third column will be D3. Okay. Okay. And so now that we've written out the global system here, now we need to fill in the global stiffness matrix. Okay. All right, and so to do this, we're going to use that kind of weird, fitting, almost like fitting in the puzzle piece thing that we did kind of in our linear algebra review. Okay. And so in this case, we have two element stiffness matrices here, and we need to basically fit these guys into the right locations onto the global one. Right? So let's start with Ka. Right? Right? Element A. And so we can see here that element A is going to be acting on D1 and D2. Okay. Okay. And so just like we've done previously, we're going to basically put a small box around the D1 and D2 slots on the global system. Okay. And so if we see from here that the first two rows are the D1 and D2 rows, and then the first two columns are the D1, D2 columns. And so what we're going to do is we're going to put a box around where they intersect. Okay. Okay. And then once we've boxed this part here, we're just going to simply fill in the elements of that element stiffness matrix. Okay. And so that's going to be Ka minus Ka minus Ka and Ka. Okay. And so just like we did kind of previously with just kind of the matrices by themselves, but now we're actually filling it in with the element stiffness matrices that we got on the previous part. Okay. Superbly. Actually, let's do orange. Okay. And so that's the first element. Now let's fill in element B. Okay. And if we go back to the previous page, we can see here that element B acts on nodes 2 and 3. Okay. And so that tells us we're going to fill in, this system on the D2 and D3 rows and columns. Okay. And so let's go back to our global system, put a box around the D2 and D3 components, just like we did before. Okay. And then just simply fill in the values of the element stiffness matrix. Okay. So we have minus KB, KB. Okay. And since we have an overlap here, see we have the overlap on the D2 spot, we're just going to simply add KB to this guy. Okay. And then everything else that doesn't have, that's not touched by these element systems, we're just going to put 0. Okay. Right. So the second step for assembly is to basically just take all of your element systems and put them into one global one. Okay. And so the key here is to put all the element stiffness matrices into the correct spots. Okay. Because if everything's not in the right spot, then you're not going to get a correct answer for this. Okay. Any questions on this? Okay. All right. So that's assembly. And so the next step is going to be boundary conditions. Okay. And so the global system that we have right now actually can't be solved yet because we haven't added any external effects. Okay. Okay. And so in this case, we have two external effects. So on one side, we have a fixed support, and on the other side, we have a load or a force. Okay. And so in general, we can categorize boundary conditions into two different categories, kind of according to what I just mentioned. But they have kind of more scientific names based on the people who discovered them. Okay. And so the first type of boundary condition, or the first category, is known as Dirichlet boundary conditions. Okay. And so the way you spell that is like this. Okay. And so the formal.
Can you pronounce it again, Professor?
Yeah, it's called Dirichlet.
Okay, thank you.
Yep. And so the idea with Dirichlet boundary conditions is that they directly specify the value of a solution variable. Okay. Right. So kind of the common name for Dirichlet boundary conditions, that's and ANSYS uses this this terminology, is constraints. Okay. Constraints or supports. Okay. And so if we look at our spring example here, we go back to our global system, you can see that inside our solution vector here are displacements, right? And so any type of boundary condition that states, the displacement must be this, those are classified as Dirichlet boundary conditions. Okay? And so as an example, we have our fixed support. Okay? Fixed support, which is what we're using in this problem, and also what we used in the ANSYS activity. Okay? And so fixed support is nothing more than just specifying that the displacement should be 0. Okay? Okay. And so any kind of support or constraint, or at least for that we'll see, those are classified as Dirichlet boundary conditions. Okay. Okay. And so the other type of boundary condition that we'll see is called Neumann boundary conditions. Okay. And so that's spelled like this. So there's two N's. Okay. And so Neumann boundary conditions are any kind of forcing or mode effects. Okay. And so Neumann boundary conditions can actually take a lot of different forms. So for structural simulations, this could be like literally just a force that you apply. Okay. It could be a pressure, which is what we did on Tuesday with the ANSYS activity, or it can be like a stress boundary condition, But any kind of, external force that you're applying, that's not that, where you're not directly specifying the displacements. Okay. And so some examples: force, load, pressure, stress. Okay. Weight is another one. Okay. Most of the times we'll ignore the weight of an object, but the weight can also apply a force onto an object. Okay. And so all of these are classified as Neumann boundary conditions. Okay. And so the reason I make this distinction is because depending on the type of boundary condition that you have, we're going to do something different with our global system. Okay. Okay. Any questions on this? Okay. And so let's apply these boundary conditions, or first let's classify the boundary conditions that we have. Right. So let me draw our system again. So I'll label all the nodes. And so we have nodes 1, 2, and 3. Okay. And then for boundary conditions, we have our forcing on node number 3. Okay. And then we have our fixed support on node number 1. Okay. Right. And so first of all, let's classify these boundary conditions, to say what they are. Right. And so remember, the fixed support is basically saying that node number 1 is not going to have any displacement. Okay. Right. And so node number 1 is fixed, and so that's what we're saying here. It's remember, any type of boundary condition that directly specifies the solution value, these are Dirichlet boundary conditions. Whereas on the right-hand side, we have a force, and since that force is like an external, load that we're applying on our springs, this is a Neumann boundary condition. Okay. Or in other words, we can say that F3, which is the force that's being applied on node number 3, is equal to F. Okay. Okay. And so now let's actually take these and apply them to our global system. Okay, so let me go ahead and redraw our global system. So we have F1, F2, F3. Okay. Then we have KA minus KA minus KA, KA plus KB. Minus KB, minus KB, KB. Okay. Let's multiply by D1, D2, D3, right? And so the way that we're going to apply boundary conditions is we're going to modify this linear system. Okay, and so let's go ahead and start modifying this guy, right? And so the first thing I'm actually going to apply is going to be the Neumann boundary condition, okay? Because that one's actually this kind of the simplest one to do, right? And so our Neumann boundary condition here states that the force that's being applied on node 3 is going to be big F, okay? And so the way that we apply that is we just take F3, which is in our global forcing vector, and we just change that to F, okay? Right, so after applying this boundary condition here, we just simply put an F onto the forcing vector, okay? And so at the same time, we can set the values for little f1 and little f2, okay? And so, since node 3 here is the only one that has an external force, node 1 and node 2 doesn't have any kind of force on them. Like there's nothing pulling on it. And so little f1 and little f2 are just going to be 0. Okay. Right. So Neumann boundary conditions are, pretty nice because they, they're relatively simple. You just kind of plug the force right into the matrix. Okay.
Can you say that again? Why F1 and F2 are 0?
Yeah. So F1. So remember, the little f's represent any kind of forcing that we're applying on those nodes, right? And so if we look back up on this diagram right here, if we look at node 1 and node 2, there's no external force being applied on those guys. So we can just set F1 and F2 to be 0.
Okay, cool. Thank you.
Yep. Okay. So that's the Neumann boundary condition. And now let's do the Dirichlet boundary condition. Okay. So the Dirichlet boundary condition is a little bit more complicated because we're actually going to have to modify the actual matrix. Okay. And the way that we modify it is like this. Okay? And so what I want to basically show you is that let's take the first row in this matrix and then actually perform the vector-vector multiplication. So let's take this first row and actually multiply by this and set it equal to that. Okay, because remember, each row in this matrix represents an equation in a linear system. Okay, and so if we actually apply that, apply that multiplication, what we get is 0 on the left-hand side. Then we have this first entry multiplied by first entry in the matrix multiplied by this first entry right here. And so we have Ka d1, okay? And then we're going to take the second entry and then multiply it by that second entry. And so we have a minus Ka d2, okay? And then we have a 0 here, so we do 0 times d3, okay? So we have 0 times d3, okay? And 0 times d3 is just 0. And so what we have here is that we have 0 is equal to Ka times d1 minus Ka times d2. Okay. So that's fine. But we actually have another equation which we can plug in for d1, right? And that other equation is given by our Dirichlet boundary condition, which says that d1 is equal to 0. Okay. So actually, let me rewrite this this equation right here into a different form, such that it looks similar to what we have on the bottom right there. Okay, but I'll go ahead and do that on the next page because it's it's getting a little bit messy here. So before I turn the pages, does anyone have any questions on this? Okay. All right. So let's take the equation d1 is equal to 0, and then let me rewrite it in a different form. Okay. And so let's do this as 1 times d1 plus 0 times d2 plus 0 times d3, okay? And all this is equal to 0, right? Or we can put this in vector form, where we can say this is equal to 1, 0, 0 multiplied by d1, d2, d3. And all this is equal to 0, right? And so if you performed kind of the vector-vector multiplication here, you end up with the equation that we have above. Okay. Okay. And so the reason I put it in this form right here is that this kind of looks like our global system, right? And so just like in our global system, we have a vertical vector here for our solutions. We have, d1, d2, and d3, right? Next to that, we have not a matrix, but we have a row of a matrix, right? And so we have this row of 1, 0, 0. And on the right-hand side, we have the result, okay? And so, what if we actually take this system that we have here and then just plug this into our global system? Or in other words, what if we take this this equation right here and use it to replace the first row in our global system. Okay. And so instead of our first row having the KAs, which we had previously, we can instead replace it with this equation, which came from our Dirichlet boundary condition. Okay. So let's go ahead and do that. So let's go back to our global system. Okay. Then let's take this first row and let's go ahead and delete it. Okay. And then what we're going to have now is the system that we had on the previous page, right? So we're going to have 1, 0, and 0. Okay. And on the right-hand side, we still have 0. And so, we're lucky that 0 was already there. But, if 0 wasn't there, then you would put a 0 with it. Okay. Right. And so what we have now is basically this first row, which we replaced. Now this first row represents our Dirichlet boundary condition exactly, right? And so that's basically how you apply the Dirichlet boundary condition, okay? And so just to kind of summarize, so just, we have two types of boundary conditions here. So we have a Neumann boundary condition and a Dirichlet one, right? And so for a Neumann boundary condition, you just take whatever force that you have and just plot that right into the forcing vector. Okay? And so that's what we did when we did this F right here, right? And so for Neumann boundary conditions, it's just one step. So it's pretty simple. But for Dirichlet boundary conditions, we have to do multiple steps, okay? And so for Dirichlet boundary conditions, we have to replace an entire row and then replace it with something that looks like this, where we have a 1 on the diagonal entry, okay, and zeros everywhere else. And then we make sure we have a 0 on the forcing vector, okay? All right, any questions on this before we do kind of another example, just so you can kind of see this in action again?
I have a quick question.
You can go first. No, you first.
No, you first, in case we have the same question.
Okay, I was just gonna say, can you explain again when you multiplied 1 times d1 plus 0 times d2 plus 0 times d3, how that came about?
Sure. Yeah, so that equation came directly from, the Dirichlet boundary condition, because the Dirichlet boundary condition says that, we have a fixed support here on this node. And so whenever we have a fixed support, we basically are saying that this node, the displacement has to be 0. And so that fixed support gave us this equation right here, which is d1 is equal to 0. Right? And so all I did when I replaced that row in the matrix was I replaced this row with this equation. Right? And so this equation for the fixed support basically became our first row in the matrix. And so the reason I have the zeros there is because I basically took that d1 is equal to 0 and then kind of expanded it for the other ones, but the other ones aren't there because you just multiply them by 0. Yeah.
Okay, thank you.
Mm-hmm. Okay. Sarah, was that your question too?
It kind of didn't answer my question, but my question was just like where we got the 1, 0, 0 row from. I think, I'm sorry, go ahead.
Yeah. So the 1, 0, 0 came from this. So we basically took our Dirichlet boundary condition and expanded it into into 3 different terms. And so we had a 1 times the d1, a 0 times d2, and a 0 times the d3. And then,
but how did you get the 0 for d2 and 0 for d3 though?
Yeah. So the zeros came from the fact that d2 and d3 aren't in this equation, right? And so we have to multiply them by 0.
Oh, that's for the d1 row.
Exactly, right.
Oh, okay, yeah.
Yeah. Mm-hmm. Yeah. And so that's how we kind of got this system here. Okay? And so the key here is that whenever you have a Dirichlet boundary condition, you're going to replace the row with a bunch of zeros and a 1, but you have to remember that the 1 has to be in the diagonal entry, right? So it has to be in this one. Okay.
So
go ahead.
oh,
Sarah.
you first.
No, go ahead.
So would plugging in 0 to d1 in that boxed equation on the very bottom, would that be incorrect?
Of this boxed equation down here?
Yeah, that one.
So this was what was originally there. So originally in the global system, we had Ka right here and then minus Ka on the second column, right? And so that equation down there is what we kind of had originally. And so what I'm saying is for the Dirichlet boundary condition, we're going to replace this equation. So we no longer need it because it's we're gonna be replacing that equation with the Dirichlet one. Yeah.
Okay, that makes sense. Thank you.
Yep. All right. Let me answer Michael's questions first, and then I'll get to yours, Josh. All right. So Michael's question is, would this problem be simpler if we found an equivalent spring stiffness, or can we not do that? You can. That's one way to approach this problem. But one thing that we can do with finite elements is that we can actually find the displacement of something in the middle, right? And so if we kind of break up our domain into different elements like this, we can find, the displacements at wherever we basically place our nodes. And so if you did this equation by finding an equivalent spring, and so you kind of replace this with kind of one giant spring, then you would kind of lose a little bit of the granularity of the solution. So, you'd be able to get the overall displacement, but maybe not, one of the middle displacements, which, in some cases you might be interested in. Yeah. Yep. Josh, you had a question too?
Yeah, so just to make sure I understand this, if we were to just for the sense of this problem, if we were to fix all 3 points, then we would get an identity matrix, basically?
Yep. So if you fix
Okay.
all 3 points, you would not have a problem. You would just have a, everything's equal to 0. So in order to have kind of a finite element problem, you have to have, you have to have at least one constraint. But everything else should either be free or should have some forcing to it, just so, you can actually solve for something. Yeah.
Right. Gotcha. Thank you.
Yep. Oh, one thing I forgot to mention. So, a finite element problem doesn't end here. Of course, what you would actually do is you would solve this linear system. But, this is not a linear algebra class, so, I'm not going to make you do any of these by hand. So that's the point where you would, use MATLAB and plug it in there and solve for the solution there. Okay. Yeah, great questions, guys. Okay, so that's kind of the the first simple example. So let's do one that's a little bit more complex, just so that you can see how this kind of works again. And this one has numbers in it, so there's actually stuff we can actually plug in. Okay, and so let's look at a system that looks like this. Right? And so just like before, we're going to have a fixed wall on the left-hand side. Right? We have one node that's attached there. We'll call that node number 1. And then we have a spring. And so this spring constant will be Ka, okay? And then this spring will be connected to a wooden block, okay? Okay. And then on this block, we're actually going to attach 2 springs to it. Just like that. And so this will be KB, this will be KC. Okay. And this entire block right here, since all the springs are attached to this block, and this block we're going to assume is rigid, we'll call this block node number 2. So node number 2 is going to be connected to 3 different springs here. And so we'll call the 2 end nodes there, node 3 and node 4. And so node number 3, we're going to assume that there's a force to the right, so we'll call that F3. And then on node number 4, we're going to assume that there's a force to the left, and that's going to be F4. Okay. All right. So let me give you some numbers for this, just so we can actually solve it in the end. Okay. And so Ka right here is going to be 500 newtons per meter. KB here is going to be 100 newtons per meter. KC is going to be 250 newtons per meter. Okay. We'll say F3 has a magnitude of 100 newtons. And F4 here has a magnitude of 50 newtons. Okay. Okay. And so we're going to follow the same process that we did before and solve for the finite element solution for this problem. Okay. Okay. Any questions on the problem setup?
Which one is node 2?
Node 2 is this entire guy right here.
Oh, okay. Thank you.
Yeah, so node 2 is going to be connected to all three springs at the same time. So I'll show you how to kind of deal with this in the linear system. Yeah. Okay. And so our first step in solving these problems is to write out the element stiffness matrices for all of the for all of the elements. Okay. Okay. And so in this problem, we have three different elements. And so we're going to write down three different element stiffness matrices. Okay. All right, so let's do element A first. So element A is connected to nodes 1 and 2. And so this is going to be F1, F2, okay, is equal to Ka minus Ka minus Ka, Ka, okay. This will be connected to D1 and D2, okay. So that's element A. Now let's do element B. So element B will be F2 and F3, because those are the nodes that are connected to element 3. Okay. Okay. And then we have the spring constant, so Kb minus Kb minus Kb, Kb. Okay. Okay. And then the corresponding displacements for that one are going to be D2 and D3. Okay. Right. So far pretty straightforward. We're just going to keep going on with this, and then we need to write one more element stiffness matrix for Kc, which I'll do on the next page. Okay. All right. So for element C here you have to be a little bit tricky. So I think at this point, the temptation is to do nodes 3 and 4 for element C, but element C here is connected to actually node number 2 on the left and 4 on the right. Okay. And so the way that we write this down is we F2, F4 is equal to Kc minus Kc minus Kc, Kc, okay, and then D2, D4. All right. And so now that we're done writing all the element stiffness matrices, the next step is to assemble, okay? And so remember, assembly, we're going to take all of these guys and put them into one giant linear system. Okay? And so since we have 4 nodes here, our linear system, our global one, is going to have 4 elements, or 4 rows, okay? And so we have F1, F2, F3, and F4. Then we also have our matrix, okay? And then we also have our solution vector, okay? Okay. And so our solution vector is D1, D2, D3, and D4. Okay. Okay. And I'm going to go ahead and label the columns here just so that it's a little bit easier for us to work with this, okay? Okay, and so now that we've kind of created the space here, let's go ahead and start inserting our element systems. Okay, and so first let's start with element A. So I'll use red here to denote element A. Okay, and so element A here is working on nodes 1 and 2. So let's go ahead and draw a box around those parts. Okay. And so element A is going to go in here. So we're going to do Ka minus Ka minus Ka, Ka. I'm going to leave a little space there because node number 2 is going to be crowded. Okay. All right. And so now let's do element B. So I'll use green for element B. And element B is going to be acting on nodes 2 and 3. Right. So let's go ahead and draw a box around that. And so there's element B, right? And now finally, let's do element C. I'll use blue for element C. And so element C here, you have to be a little bit careful because it's not going to be one contiguous block, right? Because node element C is going to be acting on 2 and 4, right? And so we're going to be basically boxing all the intersections between rows 2 and 4 and columns 2 and 4. Okay. And so one of those intersections is going to be here. Okay. And so we're going to have a plus KC. And we have a minus KC. Minus KC. And then KC, okay? Right. And so you have to be careful about those elements that, that don't have nodes that are right next to each other. And so you want to make sure you put all of these guys in the right place, okay? All right, any questions on how we assembled this, this linear system here? Okay, all right. And so that's assembly. And so the next part that we're going to do is boundary conditions. Okay. Okay. Right. So in this problem, we actually have 3 boundary conditions. So we have one fixed support. Okay. And that fixed support is going to be acting on node 1. We have a force that's going to, and we have forces that are acting on both on nodes 3 and 4. Okay. All right. And so now let's modify our linear system here according to those boundary conditions. Okay? All right. So first, let's start with the Neumann boundary conditions, which are going to be our 2 forces. But those are, usually the easiest ones to do. Right? And so first, let's apply the forcing on node 3, right? And so the force on node 3 is just going to be F3. So let's go ahead and plug that in just like that. Use a different color. Okay. So that's pretty straightforward. And then let's apply the forcing on node 4, okay? And so you have to be careful with this one because, node F3 is going to be pointing to the right here, right? Meanwhile, force number 4, F4, is pointing to the left, okay? And so, when you have something that's pointing in the negative x direction, you want to make sure that you respect that sign in your linear system, okay? And so the way you do that is to simply just place a negative out in front of that guy. Okay? And so we're going to have a negative F4. Right here. Okay? Okay. And then since there are no forces that are acting on nodes 1 and 2, we can just put a 0 in for those places right there. Okay. All right. And then now we're going to apply our Dirichlet boundary condition. And so our Dirichlet boundary condition is going to be on node 1. And so that tells us that we're going to modify the first row in our matrix. Okay. Okay. And so just like we did in the previous example, we're going to replace this row with a 1 on the diagonal and then zeros on every other entry. Okay. And then we're just going to make sure that we have a 0 in the forcing vector. Okay. All right. Okay, and so there's our linear system. Okay, and so at this point now we can start plugging in numbers, and then once we plug in the numbers, we can solve it in MATLAB. Okay, so let me show you what the numbers for this look like, and then I will show you how I solved it in MATLAB, and then we can call it a day after that. Okay? But are there any questions about how I applied these boundary conditions? So let's go ahead and plug in the numbers, and just so we can see what it looks like. Okay. All right, so let's start with the forcing vector. And so the forcing vector here is going to be the following. So we have 0, 0, 100, minus 50. Okay. All right. And then for our matrix, we have the following. So we have 1, 0, 0, 0, minus 500, 850, minus 100, minus 250. Okay. We have 0, minus 100, 100, 0, and then 0, minus 250, 0, and 250. Okay. This is D1, D2, D3, D4. Okay. And so now that we have a system like this, we can go ahead and plug this into MATLAB. Okay. So let me go ahead and switch to my desktop. Okay. All right. So let's go ahead and create a new script. So we'll just call this test. Okay. Delete later. Okay. And so now let's create vectors for let's create a vector for the forcing vector and a vector and a matrix for this stiffness matrix. Okay. Okay. So let's do the forcing vector first. Right. And so our forcing vector had 4 components. So we had 0 on the first 2 rows. Okay. Then we had a 100 in the third slot, and then a minus 50 in the last slot. Okay. So that's fine. And then our stiffness matrix was a 4x4 matrix. Okay. And I'm just going to directly specify these values. Okay. And so let's go row by row. So the first row is going to be 1, 0, 0, 0. Okay. Next row is going to be minus 500, 850, minus 100, minus 250. Okay. Next row is going to be 0, minus 100, 100, 0. Then we have 0, minus 250, 0, 250. Okay. Right. And so there's our forcing vector and our stiffness matrix. And then our solution vector is just going to be simply the linear solution to this. Right. And so remember the shortcut that we like to use in MATLAB is this / character. Okay. You don't have to have the spaces there, but I'm doing it just to show you guys what it is. Okay. And actually, let me take this off right here. Okay. All right. And so let's just double check one more time that we have all the correct values, because typos happen and they happen all the time. All right. So let's go ahead and run it. Right. And then when you run it, you can see the solution right here. Okay. And so from the MATLAB output, we can see that D1 is equal to 0.000. Okay. D2 is equal to 0.1000. Okay. D3 is equal to 1.1000. And then D4 is equal to minus 0.1000. Okay. And so what I did is I just basically read these outputs off here, and then I matched them with D1, D2, D3. Okay. All right. And so that's how you do the direct stiffness method. Okay. And so this is kind of the workflow that you can expect for these kinds of problems. So you would for these kinds of problems, I want you to set up the linear system by hand. And so you would use hand calculations to basically compute the element stiffness matrices, assemble the global system, apply boundary conditions, and then once you do that, you can take it into MATLAB and then solve the linear system. Let MATLAB solve the linear system for you. Okay? And here's just kind of an example on how you would do that. Okay. Okay. So any questions on this? Okay. All right, so that's all I had planned for today. And so, we have 15 more minutes. And so if you were having some issues with ANSYS, I'll stick around, and help you guys out. But if you're able to complete the activity, then you guys are free to go. And so hope everyone has a good weekend. Remember the ANSYS activity is due on Tuesday, and I'll see you then.
Professor,
Thank you, Professor.
Thanks, guys.
Thank you.
Professor, for the MATLAB code that you just ran right now, you don't have to define the solution vector.
No, so the solution vector will be defined after you solve the system.
Okay, thank you.
Yep.
Have a good weekend.
Thanks, you too.
Okay, so I think you might have talked about this on Tuesday, but I don't remember what you said about it.
Mhm.
But in ANSYS, I'm not able to, when I'm doing the